something about that when we were designing experiments. And you remember randomization, replication control, remember all that kind of stuff. We had a certain kind of design, and I think we called it match pair. I think we've talked about it before. What we're going to do today is, what do you do if you have this kind of match pair design? How do you figure out whether you have statistically significant evidence or not? A match pair design is when you have two related treatments. Remember the two examples we did in class? Remember, let's say I'm trying to figure out if this new fertilizers is better or not. Remember this? And then we have this greenhouse and the sun's coming in. So we tried to match together the two most homogeneous environments. I think, remember we said maybe this one and this one are most alike, so I want to compare them. Or this one and this one are most alike, and so on. Well, so after you do the experiment, how can we do a t-test to figure out whether we have statistically significant evidence or not? Another type of problem that meets this match pair design is, I don't know, let's say that you go take the SAT. And then you take this SAT class, and you learn all about the SAT and learn stuff about it, and then you take it again. Well, how can we tell if that SAT class gave you statistically significant results? Well, we would take these two, and I'd want to compare just these two. I wouldn't want to know how this person's post did against this person's pre. I'd want to just keep those two scores together. There's a relationship between these two things. Okay? It's called a matched pair design. All right, let's go through one here. Let's say it's this new fertilizer versus old fertilizer. We're going to count how many tomatoes the plant grows. Okay? Now, remember how we did this. After we've identified these two as the most alike, what's the next thing that we would do to determine who gets the new and who gets the old? Yeah, flip a coin or something. Odds, even, random digit. We need some randomization here. Okay, so that's always the next thing that you would do. But okay, I'm going to invent some things here. So let's say, boom, you got the new fertilizer. You grew 18 tomatoes. Okay, you got the old fertilizer. You grew 11. And went with these two and flipped a coin. And okay, new fertilizer. You grew 22. Old fertilizer. You grew 15. And I'm going to get these two. Flip a coin. Oh, the new fertilizer's over here. New fertilizer, you grew 10. Old fertilizer, you grew 12. Flip a coin. I got the new fertilizer here. New fertilizer, you grew 18. Old fertilizer, you grew 7. So we just spent a whole spring running this experiment on our 8 plots. Is that difference beyond a reasonable doubt statistically significant, so I can put new and improved fertilizer? Or are those kind of differences within the element of chance? That's what we're going to do. Alright, so when we're given a matched pair situation, how do we proceed? Let's go find the individual differences, and then just from those differences, let's go do a hypothesis test or a confidence interval and see if they are significant or not. So, for this particular problem, we make up a couple of columns. So we've got maybe new and the old fertilizer. What do we got here? New fertilizer had 18, the old had 11. New fertilizer 22, old 15. New fertilizer 10, old was 12. And new fertilizer 18 and old was 7. Okay, so the first thing that we're going to do is go find those differences. Okay, so let's find the differences of each. Okay, so this one minus this one, so we grew 7 more tomatoes there. This one we also grew 7 more tomatoes. And this one actually negative 2. Okay, when we do the subtraction, we grew 2 less tomatoes. And finally, the last one, we grew 11 more tomatoes. Okay. At this point, okay, don't even look at these anymore. They're done. Our whole world are these 4 numbers. And we want to know if that is statistically significantly a higher average. So let's go get our summary statistics here. What is, somebody throw that in your calculator. Give me the X bar and the standard deviation of those two. Okay, 5.75. What was the sample standard deviation of those 4?
5.5.
5.5. 5.5.
5.5.
Wow, that was unfortunate, but. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5. 5.5 by that. But here's the question. Wow! I grew on average from my sample almost 6 more tomatoes per plant, but the question is, based on that sample of 4, is that far enough away for me to say for everyone that it's new and improved? I don't know, you're shaking your head no. I don't know. Okay, let's go find out. Maybe you're right, maybe you're wrong. We got to go through the process. Okay? All right, so let's go do a full hypothesis test for this. Okay? Population parameter. I actually want you to throw a little D in there. Just kind of shows that we took a difference. It's one of those matched pair kind of problems. So I don't know, you'd say something, the true mean difference of tomatoes grown, new versus old, minus old. Put that in there somewhere too. The true mean difference of the amount of tomatoes that will be grown, new fertilizer versus old fertilizer, and the subtraction we're doing is new minus old. All right, let's talk about your null and alternate hypothesis. U sub D. What do you think our null hypothesis is going to be in this problem? What are we going to assume to be true?
The mean of 5.75.
No. We got that from our little sample. That's just a little sample. We're trying to predict for the entire population, every single plot that you can grow a tomato plant on. I'm not trying to prove anything from my little sample. So what do you think we're going to assume?
0.
0. Yeah, we're going to assume there's no difference. You got to prove to me your product's better. So we'll assume that the difference is going to be 0. And then what are we trying to prove? That the difference would actually be, in this case, greater than 0. So you got to be careful how you did that subtraction, right? How you set up this subtraction can have a great effect on whether you're trying to prove it's more or less. With me today? Okay, assumptions. Simple random sample, nothing's going to change here. This guy, nothing's going to change here from what you've done before. This guy, nothing's going to change. You go through the same analysis you've gone through before, but you're just going through these 4 numbers. We're going to do a t-distribution because the population standard deviation is unknown. We will add a 5th assumption. And we're going to say match pair. Question mark. And we'll say yes. Dependent samples. There's a direct relationship between these samples. They were related by homogeneous environments. There was a relationship there. They were dependent on each other. All right, test statistic. Not much going on here. T is equal to x bar minus mu, sample standard deviation, square root of n. Degrees of freedom is still n minus 1. Now I got a lot of you chuckleheads out there that are not drawing pictures on hypothesis tests. Are you kidding me? At this stage? I can yell at you for that. That's what I saw in the homework. And we always draw a picture for a hypothesis test to shade our p-value areas and go. All right, go to work. You got the numbers. Is no one right? That's not a big enough difference for us to be... Is 5.75 difference in the amount of tomatoes grown not far enough away for us to have statistically significant evidence at a sample size of 4? We better be pretty far away. Number 1, this is a t-distribution. Number 2, there's only a sample size of 4, so I agree with you. You better have a pretty big difference. .75 minus 0, right? We're assuming that the real mean is 0. .5 divided by the square root of 4. Our degrees of freedom for this problem is 4 minus 1 or 3. What do we got for a t-score here?
2.09.
2.09. Now what's our picture look like? Okay, we assume that the real difference is 0. We got a difference of 5.75. Turns out that is a little bit more than 2 standard deviations away. So let's go to the charts and find out how likely was it. How likely is it to go through this entire process and get a difference of 5.75 tomatoes? Is it likely or unlikely?
I had a question about your graph.
Yeah.
Would that be an acceptable graph, or would you want it more spread out?
No, that's good. Go to your charts. We're looking at 3 degrees of freedom. We're looking for that t-score. What do we got? Between
5 and 10.
Between 5 and 10%. Is everybody there? 3 degrees of freedom. It's between the numbers of, looks like 1.638 and 2.353. Everybody see that? So the p-value is between 5 and 10%. This is why you always set the alpha level before you go do your experiment. Because if I'm developing this new fertilizer, where do you think I'm setting this alpha level? Now I'm making the new fertilizer. Don't you think I want to go here? Don't you think I want to have statistically significant evidence? So I'd probably set that alpha level around 10%, wouldn't I? So that the p-value is lower. Okay. So you always set your alpha level up before if you have to make a decision. But yeah, that's probably unethical fertilizer maker. You know, they're always unethical. Okay, they're probably going to set the alpha at 10% so they get the big fat new and improved on their label. Okay, so no, this was a little questionable. That was almost there, far enough away, right? Okay, questions, comments? Matched pair design. The weird part of it, you just got to go find these differences first. Then forget about this. A common mistake you're going to make. Throw these guys out once you're done. I mean, don't erase them, but don't look at them anymore. Because some people think, oh, the sample size is 8. No, it's not. It's not 8. Once you do the subtraction, we're only dealing with 4 numbers. That's our sample size. Okay? Questions, comments? Yeah.
How do you get the t-values between 5 and 10%?
Okay, so how do I, once I've got the t-score, how do I figure out what this p-value is going to be? In fact, that's exactly what they're showing us on this picture. Remember, the p-values are the numbers across the top. Those are the percentages that correspond to that shaded region. So in this particular problem, we had 3 degrees of freedom. Okay, so you go to the 3 degrees of freedom column, and you're looking for 2.09. And it's between the 1.6 and the 2.3. Look right above there, and you see the 5 to 10%.
Okay.
Now, if this was two-sided, you have to put, this wasn't. Good. Any other questions, comments?